Very good. I think the stream just started, if I understood that correctly.
Yeah, I think we can slowly start. So, good morning, good afternoon, everyone. Thanks for joining here today, and special thanks to Bastian for accepting to give a talk in our seminar series. So, Bastian is a full professor of machine learning at the University of Fribourg, and also the principal investigator of the IDOS lab, where he's doing very cool stuff at the intersection of topology of machine learning. So he got his PhD from computer science from the Heidelberg University in Germany. Bastian, thanks a lot for taking the time, and we look forward to hearing more about your perspective of graphs and topology.
Thank you very much for having me. This is a great opportunity now to tie together some threads and even give an outlook on some things that have been going on. So the title that I use for this, let's see, research direction is a little bit a moniker and an allusion to Shakespeare's plays. So Vertex, Edge, Clique, what's actually in a graph, right? If you know that Romeo and Juliet exists as a play, and then if you don't, it's a great play to read. It's a little bit tragic, but many things are tragic, unfortunately. So there is this great line: "What's in a name? That which we will call a rose by any other name would smell as sweet." And this always reminded me about some graph learning folklore that we all might know, or some of us might know, but that we're not maybe openly talking about, and that would be what's actually in a graph, that which we will call our data by any other means would train as well. And I think this is the invocation, or the, let's say, the starting point of this whole exposition here. And I want to give you a brief overview of what we are doing in this talk. So it's pretty clear that graph learning has massively expanded in the past decade. I don't want to play a super strict and good historian here, but one of the first mentions of the message passing paradigm, or of, let's say, vestigial parts of it, occurred in 2015, actually, in the NeurIPS conference. Back then it was named differently. It's a paper by David Duvenant and others. And so since at least that time, things have been with us. Graph neural networks are a thing now. And at some point we need to take a look back, or take a step back, I should say, and think about whether we understand graphs and the limitations of our methods by now. And of course, following this law of headlines, right? Anything that is a question can immediately be answered with no. It's a little bit of a mixture of a couple of things that I hope to be able to discuss in this talk. So let's first take a look at message passing and long-range dependencies, or things that we think we know about them. So there's a great paper by Dividi and colleagues wherein they benchmark both baselines, GNNs, and graph transformers. And then they say, okay, we have these new data sets, and I'm just reading that part of the quote out loud. Therefore, these data sets are suitable for benchmarking and exploration of message passing GNNs and graph transformer architectures that are intended to capture long-range interactions. So far, so good. This appeared in 2022. But is it though? Because there's another paper by Jan Tönzow and colleagues, which appeared as an extended abstract in the Learning on Graphs conference 2023, and which is of course also available on the archive. And here Jan and colleagues say empirical evidence suggests that on these tasks, graph transformers significantly outperform message passing GNNs. It is noteworthy that across multiple datasets, the performance gap completely vanishes after basic hyperparameter optimization. So when I read this paper, this was my first what moment. So what is going on here, right? There will be more of these moments later on. But let's take a step back. Let's ignore the long-range interactions. What about the actual graphs? So surely our graph neural networks, they use the graphs, and this is useful, right? Again, here we have a paper by Maya Bechler-Speicher and colleagues, wherein they say, while GNNs have the ability to ignore the graph structure in such cases meaning cases where the graph structure might be a deterrent to the performance, it is not clear that they will. In this work, we show that GNNs actually tend to overfit the graph structure in the sense that, emphasis mine, they use it even when a better solution can be obtained by ignoring it. So that to me was another what moment. But let's continue. What about the data set? Surely the data sets are good, right? Well, you know where this is going now, right? There's a paper by Pavlovic and colleagues from 2022 appearing in SIG-KDD. Our first finding is that standard graph benchmarks cover only a small region of this graph space that GraphWorld, so the method that they propose there, is able to cover via synthetic graph generation. Again, another what moment? So even the graphs are not that great. Even the graph datasets are not that great. But the last thing we have going for us are the edges. What about those? But again, here we have Topping and colleagues. More recently, there is a trend to decouple the input graph from the graph used for information propagation. So we're not using even the real graph anymore. Again, what? So what is going on here? What do we have to do? Before we answer those questions, let me give you just a brief overview. I mean, this is trivial for those of you who have worked with graphs, but I need this to provide a basis for the subsequent discussion. So what is a graph actually? Well, the standard definition that you probably all have heard is that it's a tuple VE consisting of a set of vertices and a set of edges, which are themselves subsets of paired vertices. It's typically subsets because you want unordered graphs or undirected graphs if the set is ordered instead. So if you have tuples, you would typically say that the graph is directed. This is a graph, although actually this is a lie. This is not a graph. This is a geometric embedding of a specific type of graph. But normally, in their purest Platonic sense, graphs don't come with any node coordinates. They only come with information about the connectivity. By the way, a quick side note here, it would be fun to get some discussion points from all of you later on. You can send them to me via email or any other direct message on a social network, because I've learned that typically a lot of people prefer the term nodes and edges, but somehow it seems to be the topologist in me that likes to say vertices V and edges E, and this gives me a very nice way to remember things, but apparently this is not how it's done anymore. So if you feel that this terminology is weird, then just let me know. In any case, there's some alternative views we could take on these graphs, and I have added these little swords here because there are some slides in this talk, maybe not all of them, right, but some of them that I consider to be a little bit controversial, and this might be one such slide. So you could say that a graph can also be considered a triangulation of a manifold. You could also say that a graph is a one-dimensional simplicial complex. Or you could say that a graph is just a metric space. Or in its most puristic form, you could say that a graph is just a set system. Now, the point of this slide is not to say that these views are better or different or wrong or whatever, but it's just to show you that there's multiple ways of dealing with the same object. And it's a little bit unclear what we're talking about when we talk about graphs. And indeed, so to zoom back into this idea of where to get graphs from, how to create graphs, there is quite a lot of rich literature to obtain graphs from other modalities. So there is a very simple, I don't want to say trivial, but it's simple in the sense of it doesn't use a lot of additional information, a very simple way of obtaining graphs from point clouds that involves calculating a RIPS graph or a neighborhood graph at a specific scale. So this scale being a geometry-based parameter that tells you that if your points are within a distance of epsilon or less, then you connect them using an edge. Of course, you can also see that this actually, technically speaking, doesn't give you one graph, but a family of graphs, because you can vary that parameter, and it's a little bit unclear how to pick it. But people have created graphs with that paradigm in mind, and some of the datasets that we are still using make actually some use of that paradigm. Now, we can also obtain graphs from modalities like time series. This is a very fun visualization, a very fun technique to create such a graph-based structure from standard time series data. It's known as the visibility graph. The idea of the visibility graph is that you connect observations Ti and Fi in the graph if no other observations occur along their linear interpolation. So you take a look at the time series, you pretend that you're a little animal living on that time series, and you take a look at which other points of the time series you can see. That was introduced way back when, in 2008, by La Casa and colleagues, and it's a method to turn time series to complex networks and then analyze those and give you an information about the dynamics and about the paradigms behind them. Now, how do these graphs actually differ from the other graphs that we're typically dealing with? And this is again a little bit of an allusion to Shakespearean play, which some of you might recognize. So some graphs arise from some prior geometry, and then the attributes in such graphs can reflect this geometry, of course. Some graphs are created differently though, but when we study these type of graphs that arise from some prior geometry, we're actually studying its geometry, or we're actually studying a proxy of that geometry, right? And you could summarize this as some are born geometrical, some achieve geometry, and some have geometry thrust upon them. This is what we're doing when we collect these data sets. So now a couple of fighting claims, and I hope that some of you push back on those and let me know how wrong I am, because that's always good. This is how you learn the best. I think that we're really, as a community, not yet equipped to ask what it means to study a specific graph, because we're not making this distinction between the different types of graphs. Of course, we're making distinctions where we say, well, this is a directed one, this is an undirected one, etc. So it's not like we don't know anything. It's just that we're not really developing a terminology to deal with the types of graphs and how they are being created. And we will see that this is, at least empirically, a big problem later on. So I believe that we need to develop a language, or at least if you believe that we already have a language, we need to develop a better language for describing this type of graph data. And by treating all these graphs the same, I believe that we're making a mistake as a community and as methods developers. So we should be looking into more diversity of our methods and more diversity of our paradigms when we deal with those things. And this is now a little bit of a meta point, or of a philosophical point. So why is this actually a problem? Couldn't we just say, well, we don't care where they're coming from, we just use them and we just apply this language to all of them? Well, the problem is that language to some extent shapes our perception and cognition, or rather the things that we don't have in our language, these are things that we can't actually discuss. So Wittgenstein famously said something along the lines of, whereof one cannot speak, thereof one must be silent. If you don't like this phrasing, Donald Rumsfeld, who is not someone I tend to agree very much with on a daily basis, but he has something that he got exactly right. And this is this idea that there are known knowns, there are things that we know we know. We also know there are unknown unknowns. That is to say, we know there are some things we don't know. But there are also unknown unknowns, the ones we don't know. And I think in graph learning, and dare I say, maybe even in machine learning in general, but definitely in graph learning, I think we are in a local minimum where we are dealing with some unknown unknowns, namely this idea of what does the graph actually mean, what does it signify, and how best to deal with it. And as long as we don't know that we don't know about these issues, we are risking that we develop the wrong methods, or that we at least develop methods that are not as powerful and as efficient as they can be. So to give you a case study from my own research, because it's always best, instead of criticizing the community, let's rather criticize myself. That's always better, because I think I can do this way better than someone externally could do it. So we had this idea of looking at whether topology can help in graph machine learning. So our basic hypothesis, before we started anything, we said that, well, to some extent, graphs can be considered topological objects, fair enough. So graph learning algorithms are not necessarily aware of topological features. So for instance, there are still graph learning algorithms that have some problems dealing with disconnected components, or with cycles of arbitrary length. So the idea that we make a model aware of such features should thus probably help in improving predictive performance, because we have a model that is now aware of more things that are going on in the data, and so this should increase performance. And indeed, we did that. We had a great paper, Topological Graph Neural Networks, at the International Conference on Learning Representations in 2022, joint work with lots of people, with Max, Edward, Michael, Eve, and Karsten. And the idea was that we develop a new layer that we can use in graph neural networks, and this layer has knowledge in a certain sense of the topological features of the data. Now, we don't need to go into the details here, but the cool thing about this is it's fully differentiable, so you can just use it as a plug and play thing, like a Lego block, and put it in your neural network. We created new synthetic data sets that had pronounced topological features, because we said, well, if it doesn't work on them, then we're doing something wrong. We found indeed that we're getting high performance on these data sets, which is great. But we also found that we're getting mediocre performance on other benchmark data sets. Okay, fair enough. It happens, right? Life is a roller coaster and machine learning research as well. But it got a little bit weird when we figured out that we got actually better performance if we randomized the node features. So if we just took the graph as such, but we randomized the node features and replaced them by essentially making them uninformative. And very diplomatically, because we were unsure what we were seeing at the time, we were just writing, well, on datasets with pronounced topological structures, we found that our method helps GNNs obtain substantial gains in predictive performance. Our key sentence here was to say with pronounced topological structures. So it actually turns out that a lot of the graph benchmark datasets don't have these pronounced topological structures, which still today strikes me as weird because they are graphs. So they should have pronounced topological features, but it turns out, and this is now just beginning to fathom somehow in the larger graph learning community, that node features carry lots of information. And so in some sense, you don't always need the full graph to actually do a good graph classification, which is, on the one hand, it's good because it means that you can ignore some of the information. On the other hand, it's bad because in the sense of developing methods and models, we are focusing much more on leveraging the graph structure in a certain way. We're thinking about attention mechanisms, we're thinking about different weightings of neighborhoods and so on and so forth. We're not really thinking about saying, okay, ignoring the graph structure, what can we do with the node features as just buckets of things, right? And so this tells us that maybe we took a wrong turn somewhere, and maybe we need to step back and think about what our method should actually do. Now, this was a little bit of a what moment for us, but a smaller one. And to answer my own question now, does topology help in graph learning? Well, the big answer, the very precise answer is it depends. It depends on the data that you're looking at. This is not really a very helpful answer because a priori you might not know that, right? So you might not know what is actually in your data. And we're going to circle back to this, to a topic that I could call troubling trends. Well, I did call it troubling trends. I'm not the only one talking about troubling trends in machine learning. This is just maybe the troubling trends of my own little nook and cranny here. So one thing that we found already a couple of years back was concerning baselines. We had this great monograph, I should almost say, on graph kernel state of the art and future challenges. With graph kernels being something that preceded the graph neural networks to some extent. So graph kernels used to be hip for the kids in the audience. Graph kernels used to be hip where before the deep learning revolution, and then afterwards they became a little bit hipper again with the neural tension kernel, but they have some issues with scalability and so on, but still kind of doing well. We analyzed the performance of many of these graph kernels on benchmark datasets. So far so good. We found that histogram kernels turn out to be surprisingly effective. That's already a little bit problematic. And why is it problematic? Well, it's problematic because none of these histogram kernels use any deeper insights into the graph structure. They are just literally counting the number of different labels in nodes or in edges, but not really more than that. And still they were surprisingly effective. But no one had actually looked at those. No one, when they published graph kernels papers, they were not saying, oh, this is the baseline for the histogram kernel. No, they were just pitching their own kernel and of course some other kernels and so on and so forth, which is the natural thing to do, right? I mean, it's not, you don't always think outside the box and look for everything, right? You're just looking for the parts of the field that you're in that you know about, right? And so you're developing kernels that work in a certain way, and then you compare them to other things that work that way. Now, we're not the only ones that had some concerns about baselines. So my colleague Chen and Yusu, they developed a methodology built on random node features, or rather I should say neighborhood-based node features. They call it a simple yet effective baseline for non-attributed graph classification, with the idea being that you use this local degree profile to classify graphs, and then you train an SVM on the resulting features. Now, these features turn out to be surprisingly effective. This is already dangerous because in deep learning, we are following the paradigm that features should be learned, right? Features should be handcrafted. We left that behind in the 80s or in the 90s. We left that behind when we started doing these deep learning models. But it turns out that these handcrafted features turn out to be surprisingly effective. At the same time, they're also not using any deeper insights into the graph structure. And indeed, Chen and Yusu wrote this very diplomatically again. They said, well, most graph kernels aim to capture graph topology and graph similarity in the hope of improving classification accuracy. But our experiments suggest that this is not yet well reflected on current benchmark datasets for non-attributed graphs. In general, while not addressed in this paper, we note that understanding the power and limitation of various graph representations is crucial and remains largely open. Indeed, that was back then. We've learned a thing or two in the meantime, but let's circle back to that. Let's take a look at what we actually know about our data. Let's zoom into our data and see what we can do. So the first thing I want to ask to the community is, where do our data sets actually come from? And well, the simple answer would be, well, we just use PyTorch geometric and then we download them. But this is really there's really more to it, and I will tell you why in a minute. So if you know Lord of the Rings, you might know this quote, right? Some things that should not have been forgotten were lost. History became legend, legend became myth, and even myth was long forgotten when some poor wretch, so that will be me, trained a large graph neural network on poorly understood data. So that describes my research perfectly in more ways than one, and in more ways than I wish it would be the case. And indeed, when we look at our data sets and and the things that we train on, we typically have almost no provenance information of benchmark data sets. Sometimes if we are really, really lucky, we get something like, this data set first appeared in this paper, and then you try to find this paper, and then in the paper they briefly mention that they collected something, and this refers to a link that is long dead, and so on. But most of the time we don't even know where these things are coming from. So for instance, I tried to, I think, was it the WebKB or something like this. I tried to track this down for some time to get an understanding of how the labels were actually being generated, and it's really, really hard to find that out from the first sources. But we're still using this data set in lots of papers. So I'll circle back to that in a minute. So typically, next to the missing provenance information, so who created it and why was it created, we also typically don't have any version information. So we pretend, and I mean, maybe all other machine learners are gods and goddesses and can create a data set without an error. But if I create something, if I code something, I'm pretty sure there's a bug or an error in there. But typically we don't have a way to communicate these different versions in benchmark. So we're just training on some version of the data that people decided that's the good one now. We often don't have predefined splits either, although with big enough data sets, this is not maybe such a big problem anymore, to be perfectly frank, because you could just say, okay, well, we split like that. But with the smaller data sets, it becomes an issue. So now let me tell you, why is this provenance information actually important? So why do you need to know how the data set was constructed and for what purpose? And for this, let me briefly again give a shout out to Shakespeare, this time in the form of what we call the data drama, this with joint work with Corinna and Yillis. It's something that we tried to originally submit to the NeurIPS datasets and benchmarks track, where the reviewers were not super excited or super happy to see it. Probably this was because we wrote it in the form of a theater play. I should say that if you look at the timestamp of the paper and you think that 2024 they used ChatGPT or something like this, no, this was done before a large language model, so it's like 100% human made, which maybe explains why no one liked it. In this, we have an explanation of how data sets of co-occurrences are being created. So if you remember this, you might have experienced or seen the Les Miserables data set every once in a while. This is your standard data set when it's time to discuss graph learning algorithms, and all these data sets have as a goal to model the co-occurrences of characters in plays or in books. And what we did is we showed that there's of course more than one way to do that, and so you can create multiple co-occurrence networks. Not going into the details of how these have been created, but I just want to show that these are the same characters, the same play, but three different ways of representing them. In fact, we found even more than three ways of representing them. There's a bunch of additional classification and generation strategies that lead to completely different data. And now there are these are all valid co-occurrence networks in that sense, and I highlighted some characters that occur in Act 3, Scene 5 of the play. So that would be Juliet, the love interest of Romeo, then the nurse, Capulet, and Lady Capulet. And one observation that you can make, it helps if you've read the play, but now you have to take it on trust. So there is all these representations show that Romeo and the Capulets are interacting. They're always connected very, very strongly. But the thing is that this never really happens in the plays. If you read the play, there's almost never a direct interaction between Romeo and the Capulets because they are sworn mortal enemies. And so, in a way, what happens is that the modeling decisions, so the rules and that we use to build the graph, to build this co-occurrence network, this decision introduces new information and it introduces some kind of bias. And we were actually using the Shakespearean plays not because they are fun and so on, but also because this is one of the few data sources where we actually know what is going on. We can read the original text, right? There is no problems with anonymity because these are fictional characters and so on and so forth. So basically, with this, we get a unique view into how different creation strategies, how different generation strategies affect the outcome. And again, I'm not saying, to be very clear, I'm not saying that any of these representations is necessarily better than any of the other, but they all have different ways of representing the data. And if we were now to publish just one of them, and we were to say that, yeah, this is the co-occurrence network, have some fun and figure out what is going on with the data and solve some tasks, you would be solving a task that is based on potentially incorrect information, or at least on potentially biased information. And that is a problem. And of course, it's not only a problem for these created cases, but also for other data sets. But let's take a different look at where our data sets are coming from. Let's take a look at PyTorch geometric. And since this is being recorded, I also want to make it very clear that this is not to be construed as a criticism of the PyTorch geometric team. On the contrary, I mean, it's an open source package. It's on us as the community to support these endeavors better and more. I just want to highlight some things that I found a little bit problematic when looking over the source code. Namely, with some regular expression magic, I was just looking at all the URLs that are in the code, or rather, all the Python code that had a URL in it. Now, truth be told, whether this code is actually being executed or not, that's a different question, right? So this I couldn't check with this, but I already found that there are some interesting hosts, some interesting web addresses in there. Namely, there's ucl.ac.uk, there's a host from is.tue.mpgde, which is the Max Planck Gesellschaft in Tübingen. There are some Google Docs and some Google Drive links and some Dropbox links that are in the code. So this already, to me, looks a little bit problematic in a certain sense, because who knows who controls these data sources, right? You could do all kinds of shenanigans with them and kind of create some chaos inadvertently, right? For instance, if we look further into these dataset sources, there are also some datasets that are directly accessed using GitHub repositories. So there's nothing wrong with that. I love GitHub. I use it myself. However, these datasets are owned by private individuals or organizations. There are some people that I recognize here, for instance, Alexander Buchevsky, of course. There is also some organizations that I recognize here, like Yandex Research. But nevertheless, it might be a fair question to ask, what actually happens if one of these persons retire? What happens if one of these persons decides to remove the data set for whatever reason? What happens then? Well, I mean, we might have backups somewhere in the web archive or somewhere else, but it's really not clear how we should handle these different dataset sources. And there are some issues, because at present it doesn't seem to be the case that there are versioning or fingerprinting information, fingerprinting mechanisms in place, right? So anyone could put anything on there and claim that it's the good source of the data. What happens if we delete a repository? What happens if files are being changed? What happens if you find a bug in the graphs that you published somewhere, and then you make a new version in GitHub, which of course works, right? It's because it's based on Git, obviously, and then you publish that. You now have no way of knowing, as a user of PyTorch Geometric or of other packages for that matter, you have no way of knowing whether you're actually training on the same data. So we can't even answer the question whether everyone is training on the same data when we look at some of the papers. Of course, And this is a valid criticism. You could argue that the cases I'm describing are not that common in practice. Nevertheless, it should be something that we should be aware of. So we should at least be able to know whether there were some changes in the data, whether there have been some updates in the data for whatever reason, right? And this is something that we're not yet doing. And one controversial slide here, and again, don't see this as a criticism of the state of the art, or of PyTorch geometric in general, but there is this idea of whether all our modern digital infrastructure is being held up by a project some random person in Nebraska has been thanklessly maintaining since 2003. And this is something that we should be aware of, and that we should actually be able to handle. And I'm raising this because I don't want us to end up in a place where we don't want to be, namely where transparency and reproducibility in AI, or in graph machining for that matter, are substantially lacking. So this is really something that we should take to heart, that we should really try to focus on, that we should really try to work towards, that we don't end up in a position where our results are not trustworthy. Now, towards the end of this talk, because I want to go into the discussion phase, let's talk about improving the field. What can we actually do to improve the field? So there's certain things that we could do easily. So we could keep track of the provenance of data sets. This is already starting within Europe's datasets and benchmarks track, although there are also, of course, always improvements, right, to the status quo. So one could think a little bit more about how to actually manage this, and how to make sure that they're maintained, these data sets, and that they're being well preserved. We could and we should use fingerprinting of these data sets, so something like SHA-256, just to make sure that we're all dealing with the same data, because it's a random binary blob that you download from the internet. You want to make sure that it does what it says, right? Now, we also should think about versioning data sets and make sure that these versions are being communicated to other researchers. One thing we could do is we could use data sheets to describe graph data sets. And just one question to the organizers here, I'm seeing some kind of wild lines and annotations on this. So can you remove them somehow? These are a little bit distracting, or maybe my computer is
Sebastian,
breaking.
I think that's something you can do from your side, because I think only you can do from your side.
Okay, but I'm not drawing anything, but let's see.
Yeah, so try to disable annotations on Zoom.
Yeah, maybe someone can do that for me. So I think I already
Okay.
did that. So I removed the ones that are currently there.
Yeah, I think it's good now. Yeah.
Okay, very good. Now we could use something like data sheets to describe the graph data sets. It's work by Timnit Gebru and others, but clearly this is only just the beginning, right? We need to be aware of the issues. We need to be aware of the fact that this is potentially an issue. Now, another thing that we should do, and this is, I think, pretty clear, is to use better hyperparameter tuning altogether, right? Now, what else can we do? And this is now where I can talk a little bit about some things that we have been putting out as a research group these past couple of months. There's also, I should say, like it has kind of a sad component to it, which I'll get to in a minute. So we can experiment with new data sets. So we have a preprint out on Mantra, the manifold triangulations assemblage, which comprises triangulations of combinatorial 2 manifolds and 3 manifolds. What we wrote in this paper is that a noteworthy aspect of Mantra is the conspicuous absence of any intrinsic vertex or edge features, such as coordinates or signals. We argue that this absence renders tasks more topological, as models can only rely on topology instead of non-topological information contained in the features. So in a sense, we said that this is what makes it very, very hard to learn certain tasks. We don't need to go too much into the details of the tasks that we can address with this, but I want to give you an idea of the motivation of the provenance. So the data for this was originally collected by my colleague Frank Lutz, who unfortunately passed away very unexpectedly and very young in 2023. So Frank had been working on combinatorial triangulations for some time, and has compiled a massive amount of work, massive amount of data sets and databases, showing that certain triangulations have certain minimum properties, for instance, showing that they are that they can be enumerated if you restrict yourselves to a fixed set of vertices, and so on and so forth. So it was really a big work, a big oeuvre that he was dealing with. And he unfortunately passed away, but we are trying to carry his legacy forward with this data set and of course with other things as well. The very good thing about this data set though is that it is clean data with well-defined properties. It is in a sense mathematically pure and platonic in that it contains well-defined triangulations with well-defined properties. There's no noisy edges in there. There are no errors that can creep into that, because we can check whether the object that we triangulated, whether it's actually the right object we are looking at. It also gives us well-defined operations to refine triangulation. So basically, taking this data set, we can easily create a zillion more triangulations from it that refer to the same object, but that are still markedly different. This is known as an operation called barycentric subdivision. Again, we don't need the details for this, but we can refine it. We can turn it into something bigger. Now, we have stored this for now in a very nice human-readable JSON file. So for instance, you have here an excerpt of that with an ID, the triangulation itself, which consists of the top level elements, a dimension of the object that is being triangulated, the number of vertices that you would get. So here 1, 2, 3, 4. So we have 4 vertices. Then some topological information known as Betti numbers and torsion coefficients, and the genus and the orientability, as well as a canonical name of this triangulation, if such a name exists. Again, remember that these are 2 manifolds and 3 manifolds, so there are some that have canonical names like the 2-sphere and the torus and so on and so forth. But really the exact topological details of these things are not super important for this discussion. What is important is that it's a data set that has been leveraged from a well-defined mathematical creation process, and that is purely combinatorial in nature, that doesn't naturally come equipped with any coordinates. Or to put it like this is always what we think about when we look at this data. So this is one such triangulation visualized and imbued with geometrical coordinates. But the thing is that while these triangulations can be geometrically realized with certain algorithms, there are no canonical coordinates for them. So essentially, I could take multiple triangulations of the same object, like a torus or whatnot, and I could give you different types of coordinates for them. And when we deal with graphs or with higher order objects for that matter, we are thinking about this type of object, the one that is being animated here. But what we're dealing with in reality is we're just dealing with the triangulation as such. So there are no coordinates, no useful information for leveraging this here. And this made for quite an interesting set of hard tasks. So we asked ourselves some research questions from this, namely, how well can we actually learn and solve some tasks with graph neural networks here? Do we need higher order information? So do we need information about the faces or the tetrahedra and so on in the data? And also, of course, which tasks are useful here? And this, I should stress, is just the start of a conversation. It's not the end. So we're not claiming that we have found the best tasks or the best data for anything, but we have now a data set that does something substantially different from other data sets, in my opinion, which is really worthwhile and really useful. And there are some preliminary, and I highlight the word preliminary here as well, answers that we can give that I'm happy to paraphrase here before we go into the discussion phase. So what we observed in our experiments is that existing models struggle to learn topological properties of triangulations, including the orientability of two-dimensional manifolds, which suggests to us that new approaches are needed to leverage these higher order structures associated with the topological information in the data. At the same time, we also saw that current higher order models outperform graph-based models in our benchmarks, which means that we can at least substantiate the promises and the kind of outlook of this new trend of higher order machine learning models. But overall, it was a little bit of a mixed bag for us, right? And Again, this is meant to be the beginning of a novel scientific conversation and avenue in the field of graph machine learning. It's not supposed to be the end. So we're not saying that this data set is perfect the way it is and do all these tasks on it or else. Rather, no, we're just putting this out there as a new data source that other people can benefit from and that they can make use of for their own models. And with this, I want to end, and I want to end on a good note. So I believe that lots of the problems that we're seeing here are more of a social nature and less of a technological one. So I don't believe that we lack the means to solve them. I rather think that we lack the will or the knowledge to solve them. And I hope that we can try addressing them and try fixing them together. And also, I want to point out, of course, that a lot of people helped shape the opinions presented in this talk and adapted to all of them. And of course, if you like this talk, it's their credit. If you hate this talk, it's my fault. So with this, I want to end and want to start a discussion phase, and I hope that we can have some interesting questions now. Thank you very much for your attention.
Thank you, Bastian, for this interesting perspective. I would suggest that we have a live discussion because the spirit of the talk is such that I think if someone wants to comment on something, you can simply, for minimal coordination, raise your hand and yeah, we can continue like that.
Very good, yeah.
I mean, if people are shy, maybe I can start because I have quite a lot of questions. I totally share your concerns about the data currently used in machine learning, and I think that's one of the things that we are lacking as a community, benchmark data sets, because data sets that we're usually trying our novel algorithms on are probably not suited to this type of task. And I think overall, to some extent, we all agree on that, right? So there are some benchmark, there are some standard data sets, everyone is comparing with that, and that's enough to get the new RICS paper, an ICML paper, and we're happy with it. But there is an underlying problem with the data there. And as I said, I totally share your concern on that. What an additional concern for me is going one step further on what would be your advice if someone tries to enter the graph machine learning or topological machine learning community now, and he has a real world problem where there is some sort of graph structure, there is an underlying topology, probably not perfect, but we are in real world scenarios where there is some knowledge about the structure, and you don't have the luxury of going into synthetic data sets because there is an underlying mechanism that you probably don't know, so you cannot really shape a synthetic data set. So what would be your advice in that real world setup, basically?
I think my first advice would be to start with the simplest models first and basically increase complexity incrementally. So all too often, I mean, I'm very bad at this myself, right? So I would love to start with the biggest hammer that I can find. So the kind of the machine learning equivalent of a thermonuclear warhead, and I would shoot that at the problem and would see what happens, right? But the thing is, if you proceed like this, you are missing out on other avenues, and you're creating a lot of additional work to get everything to run, right? So you would say, okay, no, I need to use a big foundation model, for instance, right? And I need to use multiple GPUs to train, etc., etc. And whereas if you take a step back and you think about, okay, maybe I could train a very bad model first, that is maybe only using some node information without making use of the graph information as such, and then I get some kind of baseline information, some baseline performance. And critically, I think we should all be training our baselines as much as we can and as strongly as we can, because these baselines will later on tell us whether a more complicated model is actually worthwhile pursuing. And if you manage to get to, let's say, 95% of the performance with a very simple baseline, but you have only a fraction of the compute resources for it, maybe then it would even be sufficient to to say that, okay, we have solved the task, right? And all the rest is more like, okay, additional tuning for a rainy day. So that could be useful to first try good simple baselines, then start gradually increasing complexity. But then also, if you have data that you suspect to be graphical, one thing that you can do is you can start fiddling with the graph itself, and you can see how the performance changes. And ideally, if you have a method that can leverage graph information and that needs to leverage graph information for the task, then with any permutations of the graph itself, you would see radically different predictive performance outcomes, right? So this is similar to permutation testing and statistics, I think. But again, I'm the first culprit here, right? I'm the first one to say that I'm sinning myself, right? We're not doing this often enough when we write our papers, because we're operating under this deadline pressure, and then we're saying, okay, well, our hypothesis that our method is the best, so let's just see that we get some evidence for this. But scientifically speaking, if we want to really falsify that hypothesis, then we would need to send a lot of other models, a lot of simpler models into the battle as well, and see how they perform.
Yeah, I agree. Anyone else wants to say something? There are some comments on the chat. I mean, Bastian, I don't know if you're checking them.
Oh, yeah, wait a second. I can actually open that. I'm seeing this now.
Or I can...
Maybe you can read them.
I can
because
read them, yeah. I had a
think the
question
chat is
regarding the
open, yeah.
interpretation of what the graph is. I was wondering what your opinion on graphical models is. Do you think they are more interpretable since they encode conditional dependence in the data sets?
Okay, well, that's a question on graphical models themselves, right? I mean, here when we're doing graph machining, we're not really discussing graphical models in the sense of we have different random variables and we're looking at their correlation structure or at their dependencies. I mean, in that sense, a graphical model that makes use of that structure is of course more interpretable. But this is not really my forte, or really not really what I would consider to be the current core of graph machining research, right? So, I mean, graphical models have have a long and well-established tradition, in particular when you want to figure out causes and effects and so on. But this is really something beyond the problems of the data sets that we're talking about here.
Any other comment, question? Yeah.
So maybe I can ask a question. So thanks, Bastian, for the nice talk. Could you so you mentioned once that you introduced this additional layer to bring out the topological features. So how exactly can you give some more details on how that works?
Yeah, sure. So what we did is we used techniques from computational topology to leverage things like connected components and cycles, but at a level of let's say multiple scales of the data. And the funny thing was that these features, they kind of depend in a continuous fashion on the input graph and on the input node features. And so what we did is we created a layer that essentially just augments the node features of the graph with this type of information. So you can just plug it somewhere in the middle. But as I briefly outlined here, much to our chagrin, we found that this information is already contained in the node features most of the time, meaning that the datasets that we were looking at the time are not really topological by nature, because they already know a lot of they already know their own topology by just looking at individual node features, because someone created them in such a way, right? So for instance, like if you have a certain molecule, then if you know that there is a ring around a certain node, or if you know that a node is part of a certain ring structure, then you can encode this in the node feature, and then you don't really need to go through the graph to find the ring, but rather you know already that it's there, right? So kind of like we were running a little bit into this issue that our method was solving the right problem, but the data was actually already encoding that information
Uh,
as part of a pre-processing step. And that was a sobering thought, because we thought that there would be much more to gain here.
mhm. Okay, yeah, thanks.
Yeah, you're welcome.
And there is another comment in the chat. What is your opinion on signal processing and topology?
Excuse
I
me,
guess
could you
that
repeat that? I didn't get that acoustically.
what is your opinion on signal processing and topology? I guess it's a broad question.
This is a very broad question. I mean, so I think a priori these things can be put together very nicely. So, I mean, for one, I think the idea of how a signal on a manifold or on a combinatorial manifold or on a simplicial complex or whatever you want to put in this place, how that spreads and how that affects certain information in the data set. I think this is really understudied. So there's lots of potential there to do something new. What I'm personally excited about are some new kind of, let's say, diffusion processes, for instance, or also some things that make use of concepts like a flow. So similar to the differential topology concept of a Ricci flow, which starts to solve singularities in your manifold, right? It would be very, very nice to have some kind of signal processing based flow mechanism that looks at your combinatorial structures and tries to smooth certain things out, and while doing so give you information about these things. So yeah, I think it's an interesting research field that certainly has much more promise. I should say though that, in all honesty, I come from a little bit of a different background. So I'm originally an algebraic / differential topologist before I switched to computer science and machine learning. And so to me, some of these signal processing approaches are still very new, and I don't really fully I don't have the full picture yet. I don't know how to fully place them and put them together. But based on what I understand, I think it's a very nice way to deal with this type of data. Now I'm seeing the chat. Very good.
Yeah, there is a question from Yanis. Yes, please, if you can unmute yourself.
Yes, thank you, Bastian, for a very thought-provoking presentation. My question lies on creating data sets. And do you have any prescriptions on how to generate them, like robustly, like what kind of metadata should be, or contextual data should be kept when a data set is created? And do you know of data sets that actually you would trust as that you would trust to run AI and graph-based machine learning models on them from any discipline on the planet?
Yeah. No, of course. So there's a couple of things to disentangle here. Wait a second. I hope that the chat window goes away. Okay, we're gone. So first of all, how to create those data sets robustly and what information to include. Well, there are already some initiatives, I think, that deal with metadata and with how to include such metadata. I can't with 100% accuracy say what would be the best metadata to include, but certainly what I can say is that ideally your data set should be well documented in terms of different axes. So in the axis of saying, how did you create it? For which purpose did you create it? How were the features, if there are any, how they were created? What are certain things that people can do with the data set? What are some tasks that you envision? All these things should ideally accompany your data set when you interact with it. And of course, also there should be some kind of versioning mechanism. So you should be able to say, okay, this is that version, and it should ideally even be versionized and get assigned something like a DOI. So with Zenodo, for instance, you can assign DOIs to versions of your data, and you can actually make sure that people can train on the right data set. Now, as for your second question, I mean, what data sets would I trust or would I use? I mean, of course, I'm in the same situation as all of you. I unfortunately don't have a magic repository of good data sets. I mean, I'm using the benchmark data sets as much as other people. If you know some of my work, we're also just using the OGB data sets, for instance. We're using some of the TU data sets and so on. And none of these repositories, so should be made clear, the folks that took the time to create these repositories, they did a great job, right? So it's not, I don't want to come across as saying that like, oh no, all this data is bad and so on and so forth. I'm just saying that they were working with the data sets that they had at a specific point in time, and those data sets were already not very well documented. And so now we're in the place where, while we can easily create some open stats on the data, so we can say, okay, nodes, class labels, etc. What we're often lacking is the knowledge of how these graph labels have been created and what type of information went into them. So one way to solve this is we can use the recency bias, and we can use data sets that have been created more recently. So taking a look at some of the NeurIPS data sets and benchmarks submissions, for instance, there's a new data set that is dealing with heterophily, for instance, and homophily, right? So these data sets, they're typically created with a little bit more of a mindful perspective of the current community in mind. But yeah, I think it's going to be an effort that will keep us busy for some time, and we should all carefully and critically think about what is in our data before we run the models, in all honesty.
There is another comment in the chat, another general one. How do you make graph learning topology aware?
Well, I mean, there's multiple ways of doing so. So we described one in our paper, which uses a technique from computational topology called persistent homology that makes it kind of aware of certain types of multi-scale topological features. We'll go a little bit beyond the scope of this talk to discuss that. There's also other options to do that. So for instance, you could try to leverage some kind of Laplacian operator in the graph and then link that to certain features. So it all depends on the computational constraints and on the application domain that you're dealing with. So whether you can kind of afford one paradigm, one computational paradigm over the other.
Nice. Is there any other urgent question for Bastian related to this talk? I know that there might be many other questions related to his research. There is another question in the chat, but I think it's a bit out of the scope of this talk as well, about the graph edit distance in graph machine learning. But yeah, if there is any other final question on those aspects that were discussed today. If not, let me thank Bastian again. Thanks a lot for this insightful talk. And thanks everyone for being here today. And I hope to see you all in a couple of weeks for our next seminar.
Actually, 2 weeks.
In 2 weeks.
Yeah.
Very nice.
Thanks
Thank you very much for
everyone.
having
Thanks,
me.
Bastian.